Okay, so let's move on to the next colligative property, which is known as the boiling point elevation. So what we're talking about here is a situation where you have a solvent at a particular boiling point, and then when you add a certain amount of solute, the solute actually elevates the boiling point. And we can see several applications of this. For example, if you look at the coolants that you add to your motor vehicles to prevent it from overheating, this is an example of boiling point elevation because the coolant contains a solution of a compound known as ethylene glycol. And what ethylene glycol does to the solution is elevates the boiling point. So therefore, your engine does not overheat when it's added to the engine, when you add it to the radiator. If the engine gets to a certain temperature, basically the liquid or the solution will have a cooling effect because its boiling point is higher than that of water. So that's just giving you an idea as to an application of this particular concept. Okay, so what do we have here? We have a graph. Let me just explain what this graph is all about. So you'll notice that we have y-axis being labeled the pressure axis, and the x-axis is labeled with temperature, all right? And you have different regions of this particular graph, which are labeled solid, liquid, and vapor to the extreme right, okay? Now, the lines that we have here in between the regions, let me just explain briefly what they are. This line here represents the corresponding pressures and temperatures at which you have an equilibrium between the solid state and the vapor state, all right? So basically, you have the back and forth between the solid and the vapor state of the particular substance, and at equilibrium, where the rate of the back and forth is the same, is represented by this particular line right here. So on this line here, it represents where you have different pressures and temperatures where the solid and vapor would be at equilibrium. All right, then we have this line here, which represents the different pressures and temperatures at which you have an equilibrium between the solid state and a liquid state. So basically, we're talking about the different melting points of the substance existing along this line right here. And then this line here represents the different vapors, different temperatures and vapor pressure of the liquid, between the liquid and the vapor states, all right? So in essence, what we're talking about here are the different boiling points at the corresponding pressures and temperatures, all right? So the red lines represent basically the state of affairs for the pure solvent, all right? Now, what we'll be looking at is the effect on the boiling point when you add a particular solute to the liquid already at the boiling point. So when you add a solute to the liquid at its boiling point, and oh, I should say something here, very important. The definition of the boiling point, very important for you to remember this. The boiling point definition is, it is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. So we're talking about this point right here, where the vapor pressure is 1 atmosphere. The boiling point would be represented by right here, all right? So in the case of water, that would be 100 degrees Celsius for pure water at 1 atmosphere. Now, if the vapor pressure, if the atmospheric pressure changes to something down here, then the boiling point would be something down here, all right? Okay, so let me go back to this point right here. So we have the water at the boiling point here, and then we all of a sudden add a certain amount of solute to it. So what the solute will do, if you remember what we discussed earlier when we look at vapor pressure depression, the solute is going to reduce the vapor pressure of the liquid, of the solvent, all right? So what that means, therefore, is that when the solute is added, the liquid will not be at the boiling point anymore, because now the vapor pressure is not equal to the atmospheric pressure at the temperature which was previously the boiling point of the pure solvent. So in order for us to get this solvent to boil again, we need to increase the temperature such that the vapor pressure is equal to the atmospheric pressure. And when that happens, that means that there will be a new boiling point, which would be higher compared to the boiling point of the original solvent. So this would be the boiling point of the solution, which will be higher than the boiling point of the pure solvent. All right. So in other words, we will have what is called the elevation of the boiling point. All right. So the elevation of the boiling point would be the difference between the boiling point of the solution and the boiling point of the solvent. So that's what these two terms represent, right? TB, 0, represents the boiling point of the pure solvent, while TB is simply the boiling point of the solution, all right? And remember, the boiling point of the solution is going to be higher than the boiling point of the solvent, so therefore the change in the boiling point will be positive. So therefore, that's what this is saying. TB is going to be greater than TB0, or the change in the boiling point is going to be positive. And the relationship between the boiling point elevation and the molality of the solution is given by this equation. Delta TB is equal to KB times M. Now, we know what delta TB is already. M is going to be the molality. We met this term earlier in a previous video, which is one way of measuring the concentration of the solution. And KB is a constant. It's called the molar boiling point constant, or I should say the molar boiling point elevation constant for the solvent. In some textbooks, they call it the ebullioscopic constant. It's the same thing, all right? So that's the relationship between the elevation and the boiling point and the molality. It's basically a proportional relationship with KB being the constant of proportionality. Another thing I want to point out here is the units of KB. The units of KB is degrees Celsius over M. M being, of course, the molar unit, all right? You could easily the degree Celsius unit with Kelvin, right? K, all right? In some textbooks, you'll see the units expressed as K over M. It does not affect anything in terms of the actual value of the KB constant, all right? So that's basically what happens in the case of boiling point elevation. Now there's another colligative property known as the freezing point depression, which is very similar to, in some respects, to the boiling point elevation. Now it's based on the state of affairs that happens in this region. Let me go back to my pointer. In this region right here, all right? So again, we have the line here, which represents the different melting points or freezing points for the substance for different temperatures and pressures, right? And this line here, this parallel line, represents the same thing for the solution. And you'll notice that when you add your solute to your pure solvent, in this case water, then basically there'll be a decrease in the freezing point represented by this region right here, all right? So therefore the freezing point of water would be one value, the freezing point of the resulting solution would be less than the original freezing point of the water, all right? So we call that the freezing point depression. And you'll see that the in this particular case, the math is very similar with some slight differences. For example, because it's a depression, the change in freezing point when you compare the solvent to the solution would be negative, right? So TF0 is the freezing point of the pure solvent, TF is the freezing point of the solution, and because the freezing point of the solution is less than the freezing point of the pure solvent, that means that the change in the freezing point will be negative, all right? And the relationship between the freezing point change and the molality is given by this equation. The change in the freezing point is equal to minus Kf times M, which is the molality. And you'll notice that there's a negative sign here. The negative sign basically indicates that the freezing point is, the change in the freezing point is negative. So that's one, difference, an important difference between the equation for the freezing point depression compared to the equation for the boiling point elevation that we saw earlier. All right. So just to remind you what M is the molality of the solution, and Kf is a different constant compared to Kb. Kf is the molar freezing point depression constant, and the units is the same as in the case of Kb, all right? So we have Kb, which refers to boiling point elevation, and Kf, which is referring to freezing point depression, all right? Okay, so this is just a table giving you a sample of different substances and their respective solvents, actually, and their respective data with respect to freezing point, boiling point, Kf and Kb values. So as you can see here, water has a Kf value of 1.86 degrees per m and 0.52 degrees per m as far as the Kb value is concerned. We have benzene, we have values for ethanol, for acetic acid, and so on, right? So these are values which are constants. In fact, there are tables which contain them, and these are values that you're going to need to do when it comes to certain calculations, such as the one that we have right here, this question right here. So this question says, what is the freezing point of a solution containing 478 grams of antifreeze, which is ethylene glycol, which I referred to earlier, in 3,202 grams of water, and it gives you the molar mass of ethylene as being equal to 62.01 grams. So that's a molar mass. This should be grams per mole, by the way. All right, so that's a typo. All right, so in order for us to find the freezing point of the solution, this is the equation that we would need to use. The change in the freezing point is equal to minus Kf times m, right? So basically we need Kf and we need m, all right? Now Kf is given in the table previously. In a test situation, you would have to be given that information. So that is equal to 1.86 degrees per m. And the molality is what we need to determine based on information provided. So the molality is equal to moles of the solute divided by mass of solvent. So they gave us 478 grams of the solute. We have to convert that to moles. So we multiply 478 by 1 mole over the molar mass numerical value given here, 62.01 grams. And then we divide that by the mass of the solvent. Now they gave us the mass of the solvent in grams. By definition, we have to convert it to kilograms, which gives us the mass of the solvent being equal to 3.202 kilograms, right? And then we do the math, and according to my math, this gives you 2.41 m as the molality, right? But we're not finished yet, because remember the question is asking for the freezing point of the solution. So now this is where this equation comes in. We plug in the values for m into this equation, right, which is 2.41, and we plug in the value for Kf, which is 1.86, and that gives you the freezing point depression, which is minus 4.48, right? So that is delta Tf. Now remember, delta Tf is the difference between the freezing point of the solution and the freezing point of the pure solvent. What the question is asking for is Tf, the freezing point of the solution. So we can algebraically rearrange this equation to get Tf of the solution, and that is going to be equal to the Tf of the pure solvent plus the change in the freezing point temperature. So the freezing point temperature of the pure solvent is again given in the table that we saw on the previous slide, which is water, of course, and the freezing point is 0.00 degrees Celsius, and we add that to the change in the freezing point, which is minus 4.48, and that gives you the answer here, which is minus 4.48 degrees Celsius. So that's just basically an example of how to calculate the freezing point depression of a solution when you add a certain amount of solute to it. There's another example I want to show you, but I'm going to show you in the next slide. So that's it for now as far as this is concerned. Until next time.